if you are an aspirant of National Eligibility Test in Mathematics and following my videos, then I request you, please like, share my videos and subscribe my channel. We now discuss the solution of a problem from the section Ring Theory, that is broadly from the section Algebra, and this question has appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the concepts of irreducibility of polynomials in polynomial rings. And this question is from the part C. It is a multiple select question and there can be more than one answer, and this question carries 4.75 marks and the question ID is 704087. This question is suitable for the aspirants of JL, DL, TS set, AP set, IIT JAM and GATE examinations. The given question is, let f of x is equal to x square plus x plus 1 and g of x is equal to x square plus x minus 2 be polynomials in Z bracket x, that it is a polynomial ring over the set of integers. Then which of the following statements are true? We are given 4 options. Option 1, for all prime numbers p, f of x mod p is irreducible in Z by pz bracket x, and Z by pz is isomorphic to Zp, where p is a prime number, that it is a field, and this will be the polynomial ring Zp bracket x. Right. Option 2, there exists a prime number p such that g of x mod p is irreducible in Z by pz bracket x. Option 3, g of x is irreducible in q of x, is a polynomial ring over the field of rational numbers. Right. Option 4, f of x is irreducible in q bracket x. Right. Let's now discuss the solution of this problem in detail. We are given two polynomials fx and gx belonging to the polynomial ring Zx, and they are fx is equal to x square plus x plus 1, g of x is equal to x square plus x minus 2. And we have this quotient ring Z by pz is isomorphic to Zp, where p is a prime number, then Zp is a field under addition modulo p and multiplication modulo p. Right. We have fx, gx, both belongs to Zx. Right. Let's now consider the statement given in option 1. For all prime numbers p, f of x mod p is irreducible in Zp bracket x. Right. Now the given polynomials both are of degree 2. And we recall here a test, that is irreducibility test for polynomials of degree 2 or 3. For this you require a field f, and p of x, a polynomial, belongs to the polynomial ring f bracket x, and the degree of p of x is 2 or 3. This condition is a must, is necessary. Then p of x is reducible over f if and only if p of x has a 0 in f. That means if p of x has a root in f, then p of x is reducible over f. And mind you, your polynomial p of x must belong to the polynomial ring f bracket x, where f is a field and the degree of the polynomial is 2 or 3. Agreed. Now let's look at fx carefully. If you substitute x is equal to 1, then you will get f of 1 is equal to 1 square plus 1 plus 1, that is 3, and 3 is congruent to 0 mod 3. That means p is equal to 3 if you take in the field zp, you have f of 1 is equal to 0. So observe that f of 1 is 1 plus 1 plus 1 is equal to 3, congruent to 0 mod 3. Then apply this test, reducibility test. Then this implies f of x has a 0 in Z3, because we have considered modulo 3. So f of x has a 0 in Z3. When f of x has a 0 in Z3, mind you, Z3 is a field. When f of x has a 0 in Z3, then f of x is reducible over Z3. This shows that f of x mod 3 is reducible in the polynomial ring Z3 bracket x. One may ask a question, sir, what is this you say just f of x, why mod 3? Even if you take mod 3 also, polynomial remains same polynomial will be there. Agreed, whatever it is. So that means it is not irreducible. It's not irreducible for a prime number p is equal to 3. So the option 1 is not true. Let's go for the option 2. There exists a prime number p such that g of x mod p is irreducible in zp bracket x. Right. Now g of x is x square plus x minus 2 belongs to zx. Right. Again, the degree of this polynomial is 2, and we want the irreducibility over zp, where zp is a field. So you can apply again this test. Now you take 1 in any zp. That means we take p to be any prime number, arbitrarily chosen prime number, then zp is a field. Then in the field zp, for any p a prime number, g of 1 is a multiplicative identity of zp, and g of 1 is equal to 1 plus 1 minus 2, that is 2 minus 2 is equal to 0. So g of x has a 0 in zp, and this is true for every prime number p. So this implies g of x mod p is reducible in zp for any prime number p. And your statement that there exists a prime number p such that g of x is reducible in zp bracket x is false. So our option 2 is not true. Let's move to the next slide for the further discussion. We have f of x, g of x belongs to z bracket x. Option 3, g of x is irreducible in the polynomial ring over the field of rational numbers. Let's look at g of x, x square plus x minus 2. Again, we can use, because its degree is 2 and q is a field, so you can use this test. So f is a field, q is a field, and p of x, g of x belongs to f of x. Yeah, g of x belongs to q of x also is true. Correct, because the coefficients are rational numbers. Okay. and the degree is 2. And now in Q, multiplicative identity 1 is there. So g of 1 is 1 plus 1 minus 2 is equal to 0. That means g of x has a 0 in Q. So now apply this. If it has a 0 in Q, then it is reducible over Q. So g of x is reducible in Q, and thereby it is reducible in the ring of in the polynomial ring over rationals Q bracket x. So it is reducible, but your statement in option 3 is it is irreducible. Therefore, our option 3 is not true. So the first 3 options are not true. Obviously, the fourth option must be true. You can also conclude, and I can tick the fourth option. But however, what's the proof of it? 4. F of x is irreducible in Q of x. Look at f of x. F of x is x square plus x plus 1. What are the coefficients? You can say they are belonging to z, but they are also real numbers. So it belongs to R of x. It belongs to R of x. And R is a field, and its degree is 2. And what are the roots of x square plus x plus 1? We know it is omega and omega square, which are complex numbers which are not there in R. Therefore, you do not find any roots in R. Therefore, using this one, it is irreducible over in Rx, in R bracket x. R is the set field of real numbers. Therefore, f of x is irreducible over q of x, because q of x is a part of R of x. So you can say that way also. But you can also say in a different way by now recall irreducibility of pth cyclotomic polynomial. What is a cyclotomic polynomial? Pth, where p is a prime number. For any prime p, the pth cyclotomic polynomial is x to the power of p minus 1 plus x to the power of p minus 2 plus so on and so forth plus x plus 1 is irreducible over q. Take p is equal to 3. 3 is a prime number. Now its third cyclotomic polynomial will be x to the power of 3 minus 1, x square plus x plus 1, and by this it is irreducible over q. So let p is equal to 3, then the polynomial x square plus x plus 1 is irreducible over q, because it is the third cyclotomic polynomial. You are using this result and you are getting this one. So that means that is f of x is equal to x square plus x plus 1 is irreducible in q of x. Therefore, option 4 is true. Now summarizing all the options, the answer to this question is option 4. That is the detailed discussion of the solution of the problem, which is based on the concept of irreducibility of polynomials from the ring theory. Ring theory broadly from algebra. I am sure that you understood the solution of this problem, and I wish you all the best. Thank you.